All right, we're back. We're on page 329, the last page of the math analysis notes. This is a crazy accomplishment. If you have been with us all the way through, that's amazing. All right, let's see if we can do the problems though, right? So a landscape architect wishes to include, this is a very famous type of problem. Like you will see this in every calculus book, probably on Earth, presumably in different languages. A landscape architect wishes to enclose a rectangular garden on one side by a brick wall costing $30 per foot. On the other three sides by a metal fence costing $10 per foot. If the area of the garden is 1,000 square feet, find the dimensions of the garden that minimize the cost. So we haven't done a lot of minimizing problems, so now, but they're exactly the same. It's like we hope that there's only one critical point. We hope that at that critical point it's a minimum. We can use lonely critical point theorem. If not, we could potentially so it's going to be dicey. We could potentially use candidates test, or we could come up with another argument. So let's see, let's draw something first. All right, so rectangle. Try not to make it a square. I'm like dangerously close to a square there. One side of this is going to be brick. So this side is brick, right? And then the other sides are metal. So I'm gonna call this X, call this Y. So this is also X, this is also Y. You don't really need to label all of them, as I've mentioned in the past. I usually just do because like, what's it hurt? So what do we have here? We know that the area of the garden, so we're told the area of the garden is 1,000 square feet. So that's fixed. All right, so that is probably gonna be our helper equation. So the area of this garden would be X times Y, and that has to be 1,000. And then that's easy to solve for X, it's easy to solve for Y, so let's just save it and see which one is like the most convenient, if either. And what are we trying to do? We are trying to minimize the cost. Oh, I didn't get it all the way. Minimize the cost, okay? And what's the cost? The cost is $30 per foot for the brick and $10 per foot for the like metal part. So we want to minimize the cost. So let's call it C, I guess. C, which is $30 for the brick. So 30x plus $10 for the others. So 10, there's an X and 2Y that cost 10. So we're trying to minimize that. Okay, so if we expand this, we get C is equal to 30, there's 40 X's, and then there's 20 Y's. All right, too many variables, right? So we're taking basically single variable calculus, so we need a single independent variable. When it gets multivariable, this wouldn't be as big of an issue. Still kind of an issue. In multivariable, you'll solve this with something called Lagrange multipliers, eventually. Initially, you'll do it exactly the same way. But eventually, you'll learn Lagrange multipliers. Lagrange came up earlier in the notes because he is attributed with coming up with the prime notation that we currently use. So he's a big deal, right? So you'll see him in Calc 2, Calc 3. He's everywhere calculus is. So let's see. I'm going to take my helper and I'm going to solve for y because there's no really good reason. Because if I can, I'll eliminate y, just like everyone else. 1,000 divided by x. All right, so our cost function is going to be 40x and then plus 20 times 1,000 over x. So 20,000 over x. Okay, so we want to minimize it. Let's find the derivative. So c prime is going to be 40. I'm thinking of this as 20,000 times x to the negative first, so it becomes minus 20,000 x to the negative second, which I'm going to make 20,000 over x squared. Okay, so are there limits on what x could be? I mean, they're not really, actually. I mean, if you can have, I mean, if x could like not be less than 0, but it could basically be any. You could have like a 3 trillion foot wide thing that's like whatever you need to multiply it at 1,000. So it's kind of like an open interval. I don't really like that, but let's see. So C prime, let's keep going. So it's going to be 40x squared minus 20,000 over x squared. Okay, so I can take out 40. I really don't like factoring these things. C prime is, so I can take out 40. I got x squared. What is 20,000 divided by 40? 20,000 divided by 4 is 5,000. Divided by 10 is 500. So minus 500. Okay, and then over x squared. So if C prime, oh, look at me, look, running out of space here. I'm working nicely and vertically though, which is unusual. I really prefer to work horizontally. It's not a good thing, but it's just what I do. So C prime equals 0. X is either plus or minus the square root of 500, but you can't have a negative. So X is the square root of 500. All right, so what could we do? Well, there's only one critical point. I'm hoping lonely critical point will help me out on this. So what I'm going to do is I'm going to go back to, I'm going to go back here and find the second derivative. So from here, it's kind of the wrong color, but you know, live with it. So C double prime is going to be, so think of it as negative 20,000 x to the negative second. So it'll be 40,000 x to the negative third, which I'm going to write as 40,000 over x cubed. Okay. If x is equal to radical 500, that's greater than 0. We don't really care what it is, right? So we just care that it's negative, no positive. We care that it's positive. If it was negative, this would be a problem because we're looking for the minimum and we would have found a maximum. And then like, what do we do? It'd have to be an endpoint. We couldn't figure out the endpoint. So like, it would go poorly at that point. All right, let's write this up because we know the answer. So, well, we kind of know the answer. Find the dimensions. We didn't find the dimensions, but we're close. All right, so first, we're going to say that C of x has a relative minimum at x equals the square root of 500. And then we got to say why. So because C prime radical of 500 equals 0, and C double prime of radical of 500 is greater than 0, right? So that's the second derivative test. Now, lonely critical point. Since x equals radical 500 is the only critical point. I think I should say the only critical point for x greater than 0, because there were 2. So it's like the only one on our interval where we're interested in. So for x greater than 0, C of x has the absolute max. Min, sorry. It's just, you do so many maximum problems, it just gets in your head. Absolute min at x equals radical 500. Okay, so now let's actually answer the question. So we want to find the dimensions of the garden that minimize the cost. So therefore, dimensions of the garden are radical 500 by, so 1,000 divided by radical 500. If you rationalize that, you get 1,000 radical 500 over 500, so you get 2 root 500. So by 2 root 500, and then I'm going to say in parentheses, radical 500 is brick, because you do kind of want to distinguish, because like if you do the wrong dimension in brick, then your costs are like all out of whack and all that. All right, so I think that problem's done. I think what we should do is go to the calculator and like redo the problem and make sure that we got it right, or well, see if we got it right. I feel like we did. I'm gonna do new document here. So I have x times y is equal to 1,000. So then I solved this for y. That's fine. I got that the cost, so C of x, I guess, is going to be 30x plus 10 times, there's one x and there are two y's, such that, and then y is equal to this. So C of x is whatever that is. Why is it so complicated? Whatever, it doesn't matter. Derivative of this with respect to x, then we solved. This doesn't look right at all. Equals 0 for x. And yeah, I got a very different answer. Did I do this wrong? 30, 40, 30 plus 10. Oh, I did it wrong. Here we go. Okay. Whew. Thank goodness. I mean, that was like making me nervous. So c of x. That looks like what we had. Derivative. That's the thing with the calculator. Like, I'm willing to just keep going because it's like, I know that going back isn't going to be that bad. Solve the answer for x. Oh, the answer equals 0 for x. Okay, so that's the square root of 500. Rationalizing calculator all the time. Then I did derivative c of x with respect to x, but the second derivative, such that x equals the square root of 500. I got a positive, which means concave up, which means we're at a minimum. It was the only critical point on the interval, so it's the absolute minimum. So we got it. All right, so let's go back to the notes and put an end to this problem. And then I think what I'll do is come back in one last video for math analysis, and we will solve the next problem on the page. All right, so we're done, and I will see you in the next one. All right, so hope you're finding these helpful, and see you then.